So another big brain that we have, we're very fortunate to have with us this weekend is Hilairy Hartnett, Senior Sustainability Scientist, Associate Professor, School of Art and Space Exploration, Associate Professor, School of Molecular Sciences. I can't even say it.
I'll translate all that in a
Thank
second.
you. Faculty for the Center of Biodiversity Outcomes. She's a partner in something called PlanetWorks at the Arizona State University, which she's going to tell us about. So I'm very thrilled to have her here during her sabbatical, so she's doing it on time off. Thank you very much. Please welcome Hilairy to the stage.
PlanetWorks really is about envisioning a positive future. So I am an oceanographer, but I have a degree in art history. I call myself a biogeochemist. I study the Anthropocene, and I'm an astrobiologist. So if you take anything home from that, I'm an interdisciplinarian. My science sits at the boundaries between a variety of different scientific fields. I still self-identify mostly as an oceanographer, even though I've answered to all these other things. I've also recently taken to describing myself as a plein air scientist. I work outside. Every piece of research that I do is about a place, is about an environment, and that environment could be a hot spring in a river in Indonesia. It could be a saline pool in Mexico. It could be hot springs in Yellowstone. You saw my oceanography pictures before. And the fundamental questions are about what happens to carbon in the environment. I ask questions about the source and fate of carbon, and what are the outcomes of that carbon for ecosystem services, environmental health, a whole range of things. And some of these environments are actually completely man-made. This is a hot spring in China that has been visited for hundreds and hundreds of years. They've created a park around it. This is a lake in downtown Phoenix, which suffers from the problem of dam breakage and dam releases, and so the lake comes and goes periodically. This is the Colorado River in central Arizona. I had tremendous trouble getting the Colorado River project funded because it was perceived as being not a natural system. Why would you want to study biogeochemical processes in an unnatural system? And I had to make the case multiple times that these are the systems we live with now. This is where we get our water. This is the environment that we are coexisting with. We have to study them from a geochemical standpoint. I eventually did get the funding. And this is Lake Powell upstream from the river, upstream on the river. But what I'm going to do now is I'm going to recapitulate something I did with Delia in an art science project at ASU about the oceans and climate change. I'm going to use that to frame PlanetWorks as I think an initiative that we need. So the oceans are everywhere in the way we think about things as humans. They're in our origin myths, right? I love the one from the Iroquois about the earth rising on the back of a turtle from the mud. The oceans are buried in our myths about good and evil, and this is Vishnu churning the ocean of milk. There are gods and demons in here, and the pointer doesn't actually help. And there's an underlying theme about the nectar of immortality. People have been completely incorporating the ocean into the way we think about things. The oceans are dangerous. Living in Provincetown, you guys know that absolutely viscerally. Hokusai knew it too. In Arizona, I'm not sure my students get that. But I would put it to you, the oceans are also a benign planetary force. Our planet is the way it is because we have the oceans that we have. And we are an ocean people in ways that we don't always even recognize. This is a Polynesian map. It basically lines out islands and ocean currents that allow you to navigate in Polynesia. Not anybody, only people trained to do it, and that is a dying art. This is a trireme from ancient Greece that's been rebuilt in the modern age, and you can actually see people rowing this thing. It's in the stamps. We have been exploring the oceans for a long time, and maybe this isn't exploration, but it still is deeply coupled to the ocean as anything else. But I also think we've become disconnected from our oceans in ways that are perfectly explainable in the construct of the 21st century, but we need to actually see that we are disconnected too. So what does our ocean do for us? Well, it does all kinds of things. Most notably, it moderates our temperature, right? The ocean is a giant thermostat. Water is hard to heat up and cool down. It's why it takes a long time to make tea. This is a beautiful map. It came from NOAA, the National Oceanic and Atmospheric Administration. And the color in these beautiful whorls and patterns is temperature of the Gulf Stream. The Gulf Stream goes from down in the Caribbean, around Florida, travels up past us, right here, all the way over to Europe. And it's a warm water current, right? It basically moderates the entirety of the Northern Hemisphere. It's probably why Europe was able to be a sort of seat of intellectualism even during cold periods in climate, because it wasn't as cold as it could be. And all of Western civilization really at some level could be blamed on the Gulf Stream in a lot of ways. The ocean is also absorbing CO2 from the atmosphere. So this is a plot from the IPCC report. This is uptake of carbon. It's in units of petagrams of carbon. Petagrams are big. And the blue is the oceans, and the green is the land. And the thing to take home from here, this is the 1850s up to about 2005, it looks like here. And the ocean is happily taking up CO2. The land might be taking up CO2. It might be releasing CO2. There's what we call a lot of uncertainty around these numbers. And the reason the ocean is taking up CO2 is because we're giving it to it. This is the atmospheric CO2 data. How many of you have seen this plot? How many of you have never seen this plot? All right. So we measure carbon dioxide in the atmosphere, CO2, and we measure it at a station in Hawaii. Every day they go out, they actually take literally a bottle sample of the atmosphere, they take it to a mass spectrometer, they measure how much is there. And we've been doing that since 1955. And so the amount of CO2 in 1955 is about 315. This is called parts per million. It's the fraction of the atmosphere that has CO2. It's a little number. And on May 3rd, it was 409. So this is a big increase. This increase is about 30% since we began measuring it. And there's an incredible story here about what's going on. Obviously, it's going up. When I was in grad school, the number we learned was 350 parts per thousand. When I'm not thinking super rigorously, I still default to that number, and I'm always surprised when it's like, oh, right, it's 410. This is the CO2 that comes from burning fossil fuels. But you can also see there are these beautiful regular oscillations in the CO2. That's the Earth, you could say breathing. It's plants taking up CO2 in the summer when they grow, and plants releasing CO2 in the winter when they're not growing as actively, and so all the respiration that's occurring that releases CO2, just like we do when we breathe out. So you can see the planet's biosphere going through seasonal cycles. One of the things I really like about this plot is that you can see multiple processes over multiple time scales. You can see the annual wiggles. You can see the, what I'll call decadal scale increases from human activity. If I showed you a plot that goes back beyond the 1850s, you would see that it's relatively stable and flat. The world, the Earth, is telling us a story if we just know what to look for. Now, this increase in CO2 is somewhat problematic. CO2 is a greenhouse gas. It causes warming because it absorbs light from the sun, but it does other things too. It's a little bit of chemistry. How many of you liked chemistry? How many of you did not like chemistry? How many of you felt you were not taught chemistry the way you wanted to learn chemistry? Yeah, that's a problem. So I'm going to tell you a simple story. Carbon dioxide, CO2, dissolved in water is an acid, right? Your Diet Coke is acidic, your fizzy water is acidic, your dentist might tell you you shouldn't drink so much carbonated stuff, it will erode your teeth. It erodes your teeth because it's an acid. In an artistic sense, it erodes your teeth just the way when you do lithography and you put the wax resist on and then you apply an acid to the stone, it etches away the stone. Same process. Everybody okay now with acids? Cool. The acid part is this little H. It's called a proton. Doesn't stand for Hilairy. But when you put CO2 with water, you make this thing, and all these little H's, they can come back off, and that's where the acid comes from. And so this species can lose a proton. This one still has an H, it can lose a proton. The more protons you make, the more acidic the system gets. And so when we put CO2 into the atmosphere, and we say, oh, the ocean is absorbing it, what's really happening is that the ocean is taking that CO2 and turning it into an acid. It turns out the ocean has this beautiful system that we call buffering. It can take up CO2, there it is with its protons on it. And if there's too much of it, it can release some back to the atmosphere. And it can go back and forth. And it did that beautifully for millions of years until we started pressing on the acidic side, and raising the amount of acid in the ocean. So the question then becomes, how long will the ocean continue to happily buffer itself, adjusting its proton concentration or its pH? Turns out only up to a point. So here's the CO2 curve again that I showed you before. And remember I said when you put CO2 into the ocean, you make an acid. Well, it turns out the CO2 in the atmosphere, in the gas, you can see it in the CO2 in the water, that's the blue line. They go in the same direction. Now here's another tricky science problem. We use this scale called pH to measure how much acid there is in the water. I am very sorry. You want bigger numbers to mean more stuff. It's a log scale. Smaller numbers mean more stuff, so just let's take it as the CO2 goes up and the pH goes down, it gets more acidic. And this is real data from the Hawaiian Ocean Time Series site, which was near the same place where we measured the CO2. This is some of the first evidence we had that ocean chemistry was changing because CO2 in the atmosphere was changing. And scientists found this all a little disturbing. And it turns out it's not just changing in Hawaii, it changes everywhere we've gone. So here's the Hawaii data again. CO2 versus time, and pH versus time. So remember, lower numbers are more acidic. Here's the Hawaii site. But we also measure off Bermuda, and we measure off the Canaries, and the same pattern basically shows up. Different regions show different effects and different extents of acidification, but in all cases, the carbon dioxide goes up and the pH goes down. So we are basically modifying ocean chemistry, which takes longer to happen, right? If you look back here, this is increasing pretty fast. This is decreasing more slowly, but it is decreasing. It takes a while to kind of overcome the ocean's natural homeostasis. Whoops, am I going the wrong way? Yes, sorry. So the problem we now have is CO2 is increasing, pH is decreasing pretty much everywhere we go. Is this a problem? Are we going to be able to turn it back? What are the outcomes? We don't actually have answers to all of these questions. But you can start to assemble a lot of data about a lot of different climate change effects and ask yourself the question, do we think we've reached a point where things are getting harder to turn around? We know that sea level is rising. This is change in sea level, it's in inches. It doesn't feel very big, but as we already heard earlier today, 6 inches of sea level rise is a big deal, particularly here in Provincetown. Turns out it's a big deal everywhere. And it's not just satellite data, which people will argue, well, I don't know if I like the satellite data. You can go and look at every tide gauge all over the coastline, all over the US and in Europe and every place else, and you can see the sea level rise. Again, these are all plots versus time, which I keep forgetting to say. We can also see that ocean temperature is changing. So this is a plot, it's what we call temperature anomaly. That's the change in the temperature from some baseline value. And in this case, the baseline is the average temperature of the ocean between 1970 and 2000. So this is basically the time when I was a kid and a graduate student, okay? And so if it's below this line, it was cooler than that average for the late 20th century. And if it's above this line, it's warmer than the average for the late 20th century. And the other thing you'll see is that this line moves around a lot. The solid line in the middle is the average value. The envelope around it is how much above and below that line the real number might be. And even if you take the most conservative estimate of the change or the most unconservative estimate of the change, the data are all still above the line starting at about 1980. So the ocean has changed, right? The ocean is telling us something has altered in the Earth system. So what? This audience is actually far more amenable to the so what than everybody else, but I'm going to start with pteropods. Pteropods are these fabulous little creatures. They build a shell. The shell is made of calcium carbonate. Essentially, it's a rock. And pteropods are actually extremely sensitive to the acidic conditions in the water that they grow in. So here's a study that was done, now about 10 years ago. They grew pteropods in the lab in water that has the pH that was projected for 100 years from now. And after 45 days, month and a half, the pteropod shells have deteriorated a lot. These are live pteropods. This is not just that the pteropod died and its shell degraded. This is that pteropods are unable to build their shells the way they want to, if pteropods have like desires and wants, but let's assume they do. That's not good. Well, pteropods are small, pteropods are not a significant protein source. Is there anything else we care about? Here's bigger shellfish. These are clams. These are clams that were grown with the CO2 that we had before the Industrial Revolution. These are clams that are grown with CO2 approximately like it is today. And these are clams grown with CO2 that could be like the future. Today, remember, we're about 400 parts per million. This is 700 and 1500, so this is really high. And what they found is that the shells change dramatically. For the same length of growth, the shells are a lot smaller with high CO2. The shells themselves are thinner. And the hinge of the shell, which is a really good indicator of the growth stage of the clam, are dramatically altered under high carbon dioxide. And it turns out on the West Coast, oyster and shellfish industries are actually seeing significant declines in populations because of acidification. Here on the East Coast, it is not yet clear that the Atlantic is as acidic as the Pacific, but we have data from pH in this ocean that it's coming. And so it becomes an interesting question for, say, aquaculture and oyster farming in New Jersey. What do we do? How do we change what we're doing? Can we prevent this? Can we alter it? That's a hard question. Natural shellfish just won't do as well where they live traditionally. If you run an aquaculture system and you get your seawater through an intake, you might be able to choose what depth do I take my seawater in from, or what time of year or day do I collect seawater, and that would actually allow you to help compensate for this kind of thing. So there are things that can be done, but it's still that there's still this clear indication that shellfish are responding to something. There are other shellfish that we like. I'll admit that I have a deep-seated obsession with lobster that I can't satisfy in Arizona, but I have been happily partaking of it here. Turns out lobsters are more charismatic. Lobster are also probably more economically important. And the results on what are the impacts of carbon dioxide and ocean acidification on lobster are less clear. Some studies show that lobsters will actually grow larger with thicker shells under high carbon dioxide, possibly in response to the stress of the acidified seawater. There are other studies that show that that doesn't happen, so the data are not really conclusive. What we do know is that lobsters respond extremely strongly to changes in temperature, right? That their natural range changes as it gets warmer. Lobster catches have decreased dramatically in this region and have moved towards Maine. And we also know that shell disease is becoming more prevalent as a result of the temperature change. So the shellfish, the ecology, they all know that something's happening around us. We don't feel the changes in ocean chemistry directly unless an oceanographer tells us about it. But I think we need to recognize that it's happening. I've alluded to this idea that, say, as an aquaculturist, you could manage your system to accommodate the changes we're seeing in the Earth system. I'm going to put it to you that we all need to learn to manage for the future that we want. And management is a very, very loaded word. I'm actually kind of trying it out on you guys. It works with scientists. It may not work with artists at all. And I'm willing to own that. But I'm going to put it to you that we have one planet. We want to live on it. We want to live on it sustainably. And we want to keep it in such a way that we can turn it over to our children in a way that they can also live on it and live sustainably. And I'm going to argue that that's a management decision. How the heck do you manage a planet? Well, that's a really good question. And I think our planet depends on us figuring out the answer to this question. So we were beautifully set up to sort of think about what future we have. Close your eyes again. I want you to think about the future. I'm going to say 50 years out. Raise your hand if you see a positive, kind of happy, sustainable place. One more dystopian, not so sure what we're going to see, negative kind of place. Okay, so this room, you can open your eyes again. This room landed on the dystopian side. That happens a lot. I would argue that one could say that either the Pollyanna positive or the fully dystopian are both slightly dysfunctional responses to the question. There are certainly people who are in denial about the situation. I think there's a lot of despair, and I'm hoping that PlanetWorks as a concept will help to alleviate despair. I also think there's a little bit of delusion that somebody else is going to work this problem out for us, or that the scientists are going to deal with that, and I may not like them, but it's going to happen. ASU PlanetWorks is a new initiative. This is a bit of a sales pitch. This is a bit of a plea to have artists and humanists involved in what we do. Our mission is to learn how to manage Earth's future, but we need to develop, discuss, explore, and inspire the solutions to the problem that our planet faces. Our vision is nothing less than a world that works for billions of thriving people. That sounds pretty good, but how do you achieve that vision? This is basically a model for how one might get there. I'm going to put it to you that you have to start with the vision that it is possible to achieve a positive future, and it's going to take a significant amount of work and effort and commitment to get there. But the fundamental idea that it is possible to achieve a positive future is the only place to start. And so that kind of puts aside all of those dysfunctional responses to the future or the climate question. I'm not saying any of this is easy. I'm simply saying that we need to think that it's possible, or we're not even going to try. And I'm going to frame it from the standpoint that really, this is a design decision. If we want a positive future with a planet that is sustainable for the people that live there, and I mean sustainable in every way that we talk about it, that there is the capacity for everybody to live their life the way they want to with a positive outcome, that we could design for that. right? Or we could manage for that, if you like the word management. We demand it of our local and regional activities, right? We expect there to be sewage treatment, we expect there to be water supply, we expect there to be some degree of public health and safety. And we expect our cities to do that for us. We have no structures at the planetary scale, but it is not unreasonable to think that if we all agree that those are the things we want, a reasonable climate, you know, the potential to not be run over by a hurricane every 3 months in the summertime, that's a design choice. So what we put it as is that PlanetWorks is an Earth intervention decision initiative. Should we intervene in the climate? How would we do that? That seems radical, but we need to talk about what does that mean. And so these develop, discuss, inspire, explore theme is going to come through this, and I'm going to talk to you a little bit about a pilot project that we're working on and how those themes can be linked together to be more than just the sum of those things. Oh, I didn't take this out. Okay, so this is a classical diagram in the geoengineering community. It's called the Napkin Diagram because it was putatively written on a napkin in a bar someplace. And the idea is that we have a scale for temperature. Higher temperatures are up. And we have a scale for time. Time increases to the right. So the principle is that if we do nothing, temperature is going to rise over time. And that's currently the model that we have in terms of the way we manage the climate. And we have the dotted line here is some kind of climate threshold policy. You could imagine this being the 2-degree policy based on the Paris Accords, or if you're really ambitious, the 1.5-degree policy. You're never going to get to that if you do nothing. You could cut CO2 emissions. This will lower the rate of increase of this line, but all the models that people are working on right now suggest that you're never going to get below your temperature desire if you're just cutting emissions. I tend to believe those models. That's a lot of emissions cutting. I think somewhere someone said recently, we would all have to live at something like the GDP of a not very successful Eastern European country like Moldova to get to something flat. So that means everybody in the US, Western Europe, Canada would have to reduce their consumption and live at a much lower GDP level. Many other countries would rise to that level. Neither are we ready to reduce, and is the infrastructure in place for everybody else's to rise. This is a very difficult thing to achieve. It is possible, even with existing technology, though not at scale, to actually remove CO2 from the atmosphere. That is a geoengineering approach. You can absorb CO2 from the atmosphere. You have to figure out what to do with it. But you can remove CO2 from the atmosphere, which will in fact help the temperature problem. Should we do that? I see yes.
Yeah, put it in the soda water.
That's not good for your teeth. There are other ways, engineering technologies, whoops, to fix the temperature problem. One of them is called solar radiation management. This is putting aerosols, like from the volcano, into the atmosphere. We know it will cool the planet. It'll get us back to our sort of desired temperature outcome. It does nothing about the underlying cause of the temperature outcome. The CO2 is still in the atmosphere, but it will work, it's cheaper. Should we do that? Not much response.
We don't know what
We don't know what the full suite of outcomes is. Arguably, we need to learn what those outcomes are. We need to understand who benefits, who loses, how do we implement these things in ways that would be considered sustainable. They're very hard questions. I'm going to give you an example of something that might also be considered a form of geoengineering. It's a mitigation strategy as opposed to a temperature or CO2 change strategy. And it's related to ice in the Arctic. So this is a map from satellite microwave data of ice cover in the Arctic from 1979. And this is the same region from 2016. Both of these are summertime data from like September. The yellow line is the average ice cover. 2016 was a particularly bad ice year. It turns out 2015 was a bad ice year, 2017 was a bad ice year, and 2018 is not shaping up to be that great either. We're losing sea ice in the Arctic at an incredible rate. And sea ice in the Arctic is a very strong modulator of climate. Delia told me recently, you say everything 3 times, it's great. But it turns out I do. If you don't like the map of the Arctic ice, here's some data. This is ice volume, essentially the size of the ice cover. The blue data is from it's April data, so that's winter. The red data is September. And what do you see about ice volume versus time in both cases? It's decreasing. It's actually decreasing roughly linearly. That was unexpected in its own right. And if you fit a curve to this data, it's just a straight line through the data. The line intersects 0, no ice, pretty darn soon. Somewhere around 2030, maybe 2050, possibly as early as 2022. That is not encouraging. Because when you lose the ice in the summer, you can rebuild ice in the winter, but it means you're never going to rebuild enough ice to keep it around over the summertime anymore. And it's that what we call multi-year ice that provides this strong dampening of the climate warming that we have now. There are lots of reasons to care about Arctic sea ice. If you want to get into the physics, there's all this stuff about heat exchange and thermal inertia, which is really important. The fancy term for it is albedo, or whiteness. The white ice is reflective. That sends sunlight back to space and it cools the planet. You remove the white ice, you leave behind black seawater, and the planet starts to warm up faster and faster. This is the one that I think wins people's hearts and minds. We don't want to warm the Arctic to the extent that it then becomes a positive amplifying feedback. But there are also people who would argue we have geopolitical concerns in the Arctic, economic issues, potential to destabilize other climate effects like methane in the soils in Siberia, and a huge component of Arctic culture and indigenous populations, because the Arctic is not uninhabited. And one could argue that any loss of a cultural history is as bad as any other kind of sometimes you're given a talk and your brain just turns off. What do you call it when you have a type of organism that disappears altogether? An extinction event. So maybe I'm sort of over amplifying here, but I think there's a lot to these problems that don't always get talked about in this way. So we wrote a paper, yeah, that's me down at the end. I'm going to blame my colleague Steve for the majority of it, that said, what do we do? Can we do anything about ice? This was a harebrained idea that said, let's look at the physics. It turns out it is physically possible to make thicker sea ice. You can pump water from below the sea ice to the top of the sea ice where it freezes faster because it's colder, and that might, in fact, thicken sea ice in the winter. It'll melt more slowly in the summer, and could, in fact, potentially slow down this loss of sea ice. This is a peer-reviewed paper. I'm going to argue that, in fact, doing this might be a terrible idea. But just the thought exercise, would the physics allow it, was not something that anybody had discussed. It wasn't in the literature. This paper was one of the 10 most downloaded papers from the Earth's Future Journal last year for something that I think could be a bad idea. But it started a conversation among scientists, among the public, among a whole range of people about whether it should happen. And it was everything from you don't understand thermodynamics to you want to destroy the Arctic to oh my God, why doesn't anybody talk about this? This is a good idea. Like I said, I'm pretty sure this might be a bad idea, but I want to know why it's a bad idea. What's the problem with potentially trying to change Arctic sea ice? And we made a cartoon drawing of what that could look like. Absolutely not possible. But it raises a huge number of research questions. Ice physics, how would you do it, consequences for climate and citizens and culture, costs and scale, governance decisions. But if you really boil it down, what do you want to know? Will it work? Do we want it? Who decides if we want it? And how do we decide if we're going to decide if we want it? These are not science questions. These are human decision-making questions. And I'm going to put it to you that if we want to manage our planet, we have to know how to answer these questions. And I can't do this as an oceanographer. I need to work with humanists. I need to work with social scientists. And so PlanetWorks is an initiative to take projects like this and put them through the test of, is there technology? How do we discuss it? How do we explore the impacts? How do we inspire students and researchers to want to even ask these questions in the first place? So this is a type of climate intervention. You can imagine a whole range of kinds of questions about intervening in the planet, managing for the climate we want to have. Yes, removing CO2 is fundamentally the first thing we need to do. We need to do it every which way we can. But it turns out currently, we now know that removing CO2 is going to be slow. There are a lot of climate impacts we are going to feel sooner than that. Just the fact that you guys had a 100-year flooding incident for 6 inches of sea level rise sooner than we expected tells us that doing nothing is a problem, and starting later is a problem. We should start now. This initiative actually exists, and it is a collective interaction among a huge range of departments and schools at Arizona State University. This is probably only the second time we've publicly put this out there for people, and so we are working hard to try to develop partnerships beyond ASU as well. And you can see on here Earth and Space Exploration, that's geology, School of Molecular Sciences, that's chemistry, School for the Future of Innovation in Society. How many of you guys knew we had a School for the Future of Innovation in Society? They're awesome. School of Sustainability is on here somewhere. Politics, Design and Arts, English, Public Service, Geography, History. It's a truly interdisciplinary endeavor. Oops. So what do we actually do? I mean, this is easy to talk about, and you can say, oh, well, there are a bunch of academics who are just kind of noodling around about what you could do. So we have a model for how to think about ideas, and it involves convening discussions across disciplines, selecting and advancing ideas through a community-driven process. Who wants to do stuff? Who has the energy and motivation? Which ones seem to be the most fruitful or to have the most potential impact, and how do we kind of decide that? That's hard. Assembling teams to incubate these ideas past their sort of early stage, gee, wouldn't that be cool? Turns out that requires money. And we facilitate these pilot projects promoting research, and we work hard to try to obtain funding to do this stuff. And it is a cycle. You can't just stop after you've gotten money for the first project. You have to ask what happens next. You have to ask if it worked. But I think this is a model that doesn't map exactly to the standard scientific model. It's not completely dissimilar from the scientific model, but it has a much more broad-based and somewhat community-based structure to it. And scientists are okay with it, at least the ones we've talked to on campus, but they're baffled by it. That's okay. So the 4 pieces of PlanetWorks, I'm not going to go into gory detail. One of them we call the Earth Intervention Collaboratory, and this is the one about developing technological and sociological solutions to problems. This is where we're evaluating feasibility and risk, developing pilot projects. The ICE project is one of these. Another example is the ASU Center for Negative Carbon Emissions, where we're actually, Klaus Lochner is a colleague of mine, he's building a resin that absorbs CO2 from the atmosphere. He talks about it as building artificial trees, so that like trees take up CO2, his CO2 absorbing compounds could do the same thing. Still have to figure out what to do with the CO2, but this is a technology that could be scaled up. Like solar panels on your roof, you could have CO2 absorbers on your roof. That's a pretty compelling idea. Oh, yes. Little sidebar about art and science, and it's not mine. I stole it off the internet, but I like it. Paul Hargraves, who I actually do know, is a biological oceanographer, and he has been working with Faye Darling, who is an artist. These are SEM images of plankton that she has then gone and colored, and there's a nice website about this stuff. But the particular two plankton that I chose, this guy over here is a coccolithophore. He makes a shell that is calcium carbonate. This one is a diatom, and I should have made him he and her she, but she makes a shell that's silica, glass more like your windows. And their chemistries are quite different. They can live in similar parts of the ocean. And there's a team at ASU that's now thinking about whether growing them together, what we call co-culturing, might be a way to take up CO2 and accommodate the acid that's created when you do it. There's all kinds of challenges to this. Turns out growing any kinds of plankton in culture in the lab isn't quite the way it works in the ocean. But it's an interesting research question and a way to try to apply biological oceanography to the CO2 problem. All the technological solutions in the world are not going to do anything if people do not actually buy into it or understand the outcomes or the potential ramifications. And so the next piece of PlanetWorks is what we call the Stewardship Studio. And we envision the studio as driving discussions about planetary decision making, where we actually want to engage policymakers and funders and the public to shape the narratives about Earth intervention. Should we do it? Do we want to? What are your concerns versus your concerns? And ultimately, we want this to feed back on policymakers. We want them to know about what people think and the kinds of ideas that are happening and the decisions that we think we might be able to actually handle, right? Some decisions might not be something we can deal with. But the studio idea is that it literally is a space where people can come together to work with data, to work with stakeholders, to have conversations that's separate from everybody's sort of home space. And we're already doing that a little bit through interdisciplinary workshops. This is my colleague Cynthia Celine, who actually Delia did mention yesterday. And we have been having what we call planetary design conferences. Most recently it was the one we called Climate 3.0. We are currently in Climate 2.0. This is the climate that humans have changed. Climate 1.0 was whatever the Earth was doing before we had the Industrial Revolution. And ASU stood behind this. This was a panel discussion. That's me before I cut my hair. The university president and Andy Revkin, who used to write for the New York Times, he's a science writer. This was an evening event for the public. And then the rest of the workshop was scientists and scholars from all across the university doing a visioning exercise about what future we could have if we wanted to. We wrote sort of newspaper headlines about things, and we had an artist who was there basically trying to capture the work we did in this workshop visually for us, and they were quite spectacular. And now we can actually, I use them to teach one of my big classes, sort of. And these were, sorry, I'm going to open both hands. Big wall size imagery and graphic sort of facilitation of our workshop. And the answer we got from a bunch of scientists was that, yeah, positive futures are not something that people are unwilling to think about. So if people are willing to think about it, we simply need to nurture people's willingness and abilities to think creatively about what the futures could look like. And so that's going to involve technology development from our Collaboratory, this Stewardship Studio to build the kinds of discussions and conversations we need. Another outcome of something like the Stewardship Studio could be an Earth intervention analysis report. And this is modeled on all kinds of reports, whether they're from the Baltic Eye in the North Sea or other kinds of environmental reports. But what is the status of Earth intervention thinking as time goes on? We don't think about that. It's hubristic to consider that we could intervene in the planet. Well, we've already inadvertently altered the chemistry of the planet. So why can't we consider whether we could manage the planet for something better? I think we can think about that. Obviously, a lot of us are research scientists. We envision that part of this is a center for actually thinking about coevolution of the Earth and human systems, and how do we write better models and better frameworks for actually beginning to understand how to predict and understand the dynamics of those systems. That sounds great. That's extremely hard. Coupled human system, Earth system models don't really exist. We can imagine that these are beautiful integrations of things based in game theory and object-oriented coding with geophysical models. If we want to understand what the climate is going to look like in 100 years, we need to do better than just say, population will increase by a factor of this, GDP will go up to this. That's what current climate models are based on, right? They're based on the idea that economies grow and CO2 gets produced. I think we can do better. There are a lot of people at ASU that are deeply interested in these kinds of models, and they're hard, right? Just the physical structures of those models are different from each other. It isn't that they couldn't be put together, it's that it's going to take work to do it. But it also involves understanding observations of our past and thinking about how those will inform future change. And I would argue that forecasting is probably overstating it, but it would be really nice to know if we decided to moderate ice and we decided to change CO2 emissions in this way, what would the outcomes be? We deserve to have answers to those kinds of questions, and the scientists and the social scientists, I think, are ready to do that kind of research. We see some pieces of this kind of trying to understand decision making. This is a slide of the desert that's supposed to remind me that there are plenty of examples where environmental stress, which we might assume will cause conflict, actually can be worked out quite amenably. There's a situation in the Middle East where there is a water supply problem of sort of first and worst order. And the ultimate decision was that they were going to build a desalination plant in one country to help provide water to another country in a kind of collective action way. And the underlying kind of theory here is that people can start to consider things like water, or possibly temperature, a global commons. And that provides a different framework and theory for how do we talk about it, how do we think about it. And there are plenty of organizations that are trying to work on these kinds of things, and these models are not unobtainable. There's no money for them, but they're not unobtainable. I realize that sounds a little bit contradictory. And maybe the most important part of this, and one of the things that I think makes PlanetWorks different from a lot of the other NGOs, we are in the middle of a big university. We have a mandate to teach, right? Or inspire. And so some of the things that we're working on the education side are a certificate program in what we might call it planetary decision making or planetary management. You could imagine it as a certificate that a geochemist could take in addition to their degree, or a sustainability student, or someone who studies law. It's a framework for trying to understand these very large-scale problems and the complex, sort of multifaceted things that go into trying to figure out where do we begin to look for solutions to these problems. One of the things we're doing in this realm is partnering with the American Geophysical Union, which is a professional society for geoscientists. They have the Earth and Space Sciences Digital Teaching Network, and we're building modules for them that basically help to, this is K-12 stuff, not higher ed. We want to provide slightly more sophisticated kind of carbon footprint tools, ways of thinking about decision making on climate outcomes. So PlanetWorks is just getting off the ground. We have a couple of pilot projects. We have a big vision for integrating humanities, social sciences, engineering into these new ways of thinking about conceiving the problems, talking about the many stakeholders, bringing stakeholders into the conversations early as opposed to late. And training students to think this way, right? Sustainability is already doing this. Think about sustainability as often focused at the local or the personal level. We need to also think about sustainability at a planetary scale. And Earth scientists are in a particularly good position to help motivate that conversation. That's where I come in. But we absolutely have to have people in the conversation who respond as philosophers, or who think about politics, or who think about ethics, or who think about the economics of these situations. But I think it's in our hands to do something about it. And I hope I've given you an idea that one university's idea is to create a multifaceted approach to actually starting to address these things. It's framed in specific pilot projects, but premised around the idea that you have to approach them interdisciplinarily to begin with. I think that's it.